how do we get our students to solve one-step, two-step equations so that they are more fluent with that process instead of memorizing procedures, memorizing steps? Often I've found myself in the past trying to tell students to, we have to add both sides. We have to add these things to both sides. Think of the balance scale, and not actually trying to get our students to become more fluent with the operations of why we add, why we subtract. What does that look like? We're going to talk about that in this video, and we're going to give you and your students 3 different models that will help them become more fluent when solving two-step and one-step equations. Here we go. Hey there, Math Mo Makers. John here from Make Math Moments, and I want to make sure that if you have not yet subscribed to this YouTube channel, that you hit that bell, you hit that subscribe button, you click all notifications so that you get notified when we have new videos just like this one. So in this video, we're going to talk about solving two-step equations, and I want to jump right into it. I was teaching my class today, and I was working with solving two-step equations, and I wanted to share the success that I'm having over there because I'm finding my students to become much more fluent with operations. And when we introduce, an equation that is a little bit more tricky, you know what I'm talking about? Like when I all of a sudden put some integers in there, we got some negative values. How do we deal with those? Students are kind of get stuck in a rut and think about how those procedures help them. But I want them to think more fluently about what's happening, what the numbers mean. So I want to give you 3 models to do that. The other thing is when we involve fractions into there too, with a coefficients that are fractions, how do our students think about that? Like they get hung up on some of those procedures. So let's aim for fluency, which means comfort level with working with numbers and number sense. What does it really mean? Let's jump right in. Let's talk about 3 models right here. So I've set up my Mathagon page here. I'm going to use to model behind me. And the 3 models here I've outlined that we're going to talk about. And I'm going to go through some examples, walk through them, what my students will do, what I get my students to think about while they are using each of these models. First model we're going to look at is the double number line, which is the jack of all trades tool. This is one of the most useful tools I have in my grade 9 class here in Ontario. We used it previously before we getting into solving equations. We've used it previously for solving proportions, using it for ratios and equivalency. We've got a lot of comfort already on the double number line, so we're going to use it here as well to solve two-step and one-step equations. Then we're going to jump over to the bar model, which is really, I'm going to show the similarities to the double number line because it is very similar. Then we'll jump into Algebra Tiles and show that we also have another video fully on solving equations with Algebra Tiles and fractions. We'll put that link in the notes here. At the end of this video, we're going to share with a problem-based lesson that we use to help facilitate the use of these models while solving two-step and one-step equations. We're going to talk about that particular problem, where you can find that to run in your classroom. It does a great job of nudging students to use the models. That's a question we get asked a lot, is students will say, well, they don't use the model. Sometimes we have to phrase the questioning in a certain way that kind of pushes them to use one of these models. So first, let's solve a one-step equation here. I'm going to solve it with each model just to give you a sense of what that might look like. So I'm going to zoom in here to my double number line model as my first. So what we're going to do with our double number line model is set up a number line. Pardon my ugly wonky number line here. I got a number line here. Now that number line is going to stretch onwards both sides. I got some just tick marks here to give myself some moving room. Now I'm going to solve. Let's solve this equation. Let's see. Let's solve 6x equals 24. Let that be the first one-step equation we're going to solve across all models. For example, put it on 0 here. Where is 0 on the number line? And then we'll put 24 somewhere along this number line, like right here. Let's put 24 right here on the number line. And I'm showing you how to use the model. You're going to want to have your students use this number line model, and I'll give you a progression that I've used to help them use that number line without a lot of your assistance after I do this example here. So if I'm solving 6x equals 24, I'm going to put 24 on the number line. So this distance here is 24 units long. And then I have this equivalency that up on the top of the number line, I have this relationship between 6x and 24. So for every 6x, 6 times this unknown number, I get 24 units. Okay, so we've got this. Now, here's where the fluency comes in with the double number line, is that we don't want to just train our students to see, when you see this on the double number line, you take 24 and divide by 6, like that is no different than, say, going back here and going, oh, I'm going to solve this. It's a one step. Oh, what do you do with a one-step equation? We're going to do the opposite operation here, which is a valid technique, is opposite operations. It is the rule of why this all works, but dividing both sides by 6. I just don't want to get into I want my students to become fluent, not just memorize. Okay, so think about the number line is we can ask, like, where else can you put pieces of this 6x or 24. So for example, I like my students to think in benchmarks, like where would half of that go? Where would double that go? So you could even say, like, well, if I double it, like that would give me 12x. Like all of a sudden I have 12x, and that would be double that, which is 48. So I've doubled this. Or I could say, you know what, let me half this. Now, if I half this, does this help me out? So for example, what is half of that? So I place half on the double number line here. Now I should probably have changed some of my scale here. But half of 24 is 12 on my number line. And that makes sense. Like that's some sense making and building that is going to make and hit home with a lot of your students. And then what is above it? Well, what's half of the 6x? Like if I don't have 6 times the unknown number, I have half of that. I have 3 times my unknown number. And so now I've placed that along my double number line. Then you can even go further, be saying, like, well, what else? What other benchmarks can we place here? How about a third of that, or one of those? Where does 1x go now? And so then you can say, look, well, this relationship, right, is a third of that, or I've divided by 3 at that point, and therefore I want to also a third that value down here on this equivalency. And I now have a relationship that says, well, one of this x must be 4. So 3 times 4 is 12, 6 times 4 is 24, 12 times 4 is 48. I've got this now relationship that I've just shown along the number line. I've become fluent along this number line that says the x is 24. And notice, it gives the kids the freedom that not just to look at these two numbers and say, I have to divide by 6. Notice we put in, hey, I know half of that is this, and then I third this. Now, are kids going to go, okay, well, I want to go from here to here right away? Awesome. We can divide by 6 right there. That might be the most, like, the quicker method to get there. And therefore, I can divide this one by 6, and I will get 4 right away. That also can work, right? But you could also ask, students might start to build in other values. Maybe some student had solves for a different value of x along the number line. But the important part here is that we're building fluency along the relationship, the multiplying relationship along this line. And also we'll see in a minute, like, what happens when we have an adding relationship along this line. But I've got this now statement here that says x equals 4. But I halved this equation first, and then I thirded it after that. Which is the equivalency of 1/6ing it right from the get-go. All right, so that was the double number line. I'm gonna do a few different equations along this, but I do want to solve each of these using the different models. Okay, so let's move along here and look at the bar model. Bar model is actually a glorified, or maybe not glorified, double number line. The bar model suggests works on length, just like the double number line works on length. So we might say, like, one long bar is worth 24. I'm going to solve the exact same equation, folks. And then that says that 24 unit long bar, or length, is the same as 6 times an unknown number, or 6 groups of an unknown number. So you might also draw a second bar that's broken up into 6 equal sections. And each of these sections is an x unit length. And so I'm just modeling, that's the model of a 6 times x equals 24. Notice the equivalency is the lengths are the same in the model. So we have 24 units on top. We know that whole length is 24, and then this 6 times an unknown number is also 24. They have the same length. And so then, because you've got these overlapping models, you can start to go, okay, well, it's very natural to think I should divide the 24 up into 6 equal sections. So a student might just take 24 and straight off divide it by 6 and get the 4 right away on this bar model. I do want to point out the similarities over here between the two models. The bar model is sitting inside the double number line, or vice versa. You can see the 24 units long right here. So for example, if I take from 0 to 24 units and draw this rectangle across these units right here, then you can see the top part of the bar is one of the number line, one half of the bar model, and the top or the bottom part of the number line is the bottom part of the bar model, and you can divide them up. Like there's 1x, that's equal to 4 units long. And then wait, there's a 2, I could even write 2x right there. 2x's is another 4 units long. 3x's is another 4 units long. And I could put 4x here and 5x. So let me add the 4x and 5x here. And I've sectioned that. That's another 4 units long. And that's another 4 units long, and so on. You can see that bar model is sitting on the double number line. It's a shortened, I guess, version of the double number line. My personal preference is to use the double number line because it's been useful in proportions, and it's useful in obviously adding, subtracting integers. We've used it a lot already. So my tendency is to go with the double number line, but the bar model is nice to have a look at too, and I suggest showing both. All right, last one over here is let's solve this same one with Algebra Tiles. So again, we've said we had we have another video on Algebra Tiles and solving equations with that. I suggest you check those out. We have lots of different examples for that. So for example, let me just make my 6 x's to represent this. So I have 6 unknown numbers. All right, I've got my 6x. I'm going to make my 24 here. All right, and so normally what I like to do when I'm working with my students and having them work with Algebra Tiles is you almost have a line. That's the equivalency. You say, okay, this side is equivalent to this side. This is that balance method. Solving with Algebra Tiles when you have a one-step equation is to look at, okay, well, I want 1x, so let's divide these 6's into single groups of 1. That's the equivalency of dividing, this side by 6. That puts 1x in each group. We do have to map, 1 to 1. We want this this fair sharing happening here. So that's the idea of what's happening over here. We want 1 to go in each group. We want the equal number in each group here. How many x's? What is an x value? And it looks like I doubled too many times here for when I was duplicating all my tiles, so I apologize for that right there. But as you can see, fair sharing, I've just distributed 24 single tiles into 6. So the idea here is fair sharing, but you can see that it can be tedious with the algebra tiles, which helps reinforce the abstract ideas of, say, dividing them and saying I have 24 is the same as 6x. Well, I'm going to divide those 6 up into equal groups. That's why I get 1x in each group, and divide those 6 to match, and I get 4 in each group. There we go. Okay, so let's do one more example here, folks, on solving, say, maybe a two-step equation that's a little bit uglier than what we've seen here. Okay, so let's solve this one. Let's say we're solving 3x minus 5 equals, I don't know, 13. How about we'll make some nice numbers here, somewhat nice. We'll do an ugly one as our third example, where we get some fractional results and negative results as well. Okay, so on our double number line, again, I'll draw it. I'll place 0 somewhere. There it is. There's 0. And then I'm going to place 13. Let's put 13 maybe here. I don't know. You know your students, you're just going to encourage them to place it wherever. And then you can extend your number line if needed. I'll place this equivalency right up here. And again, we were looking for fluency. This is the main goal of using these models, is you want your students to become comfortable with the operations around these values and big ideas of solving equations. All right. So again, what you could be thinking about is I could go look at, if I half this like I did last time. Remember, thinking about fluency, if I half this, I get an ugly number, which might be okay, but then I'm going to get half of this. Like, how do I take half of that? That right there gets tough to think about, which makes me think that maybe there's a more clever way to think about this. Okay, so but if I double this, right? If I double this, that's over here. This length right here has been doubled. I could say, well, that's equal to 26 if I double it. Does that get me any closer? That's a multiplying relationship. I tend to encourage my students to think, where is the 3x by itself? Because if we've already done a one-step equation, we knew that, hey, thinking about where this 6x was, we could do the halving or the thirding or the sixthing. So we want to use that strategy, but I do have this -5 here. So where does 3x go on my number line? Does it go to the right or to the left of this placement right here? If I don't have this -5, imagine this -5 wasn't there. Would the number, like, would this 3x be more than 13 or less than 13? That's an important distinction. That helps them think about the fluency along this line right here. Like, if I put 13 here, does that make sense? Or not 13, but if I put 3x here, this makes more sense because this thing is 5 less than this thing, right? The relationship, the adding and subtracting relationship between these two is this thing is 5 more than that. If I would have to add 5 to this to bring this value to 0. Therefore, I have to add 5 to this to keep my equivalencies going along my number line to bring, that thing to 0, to make it just a 3x. That gives me 18 right here. Hey, look at this. Now I'm at that space where I have my 3x equals 18. You could be doing this on the side here to show what we just did. Well, look, we added 5 to both sides here, and that now we're at this 3x equals 18. And I could half it. I could get, 1.5 x's equals 9. I could double it and get a 6x equals 36. Or I could third it, right? I could third it again, and a thirding of it will bring me here, and I get 1x if I divide everything by 3, and I get a 6 when I do that. I've just divided by 3 or thirding it, but I had the flexibility to double if I wanted, or to half it if I needed to, and then move along that number line. Therefore, what did I do? I just divided by 3 here, and I divided by 3 here, and 1x is 6 in this case. So again, encourage your students to use that number line and think of that flexibility there. All right, moving on to the bar model. What's this look like on a bar model? Okay, so I've got 3x, but I'm going to take away 5, and that's equal to 13. So what does that model look like with subtraction here, or in the equivalency up to 13? That's an interesting model here. So I'm going to draw one of the bars, and I'm going to say that's 3x, 1x, 1x, and 1x. Since I'm taking away from 3x, that's reduced, right? I'm reducing 3x by 5. So let's say that distance right there is 5 units long. I've said that distance is 3x, but then I go backwards 5 units, and then that equals right there 13. Here's my bar model. Okay, so on my bar model, I've got, since this was back 5, I might want to think about, okay, how do I solve this when this is like a negative space, right? That's what's happening here, is negative space. We'll want to, if we have 3 of these x's as the full space, then notice you can think about adding these two together. I would have to add 5 to bring it back to a full amount, which gives me my 18. So this distance here is now 18, and I'm at that spot where 3 of these x's equal to 18. Oh, I can divide the 18 up into 3 equal sections. This gives us 6 in each section. So bar model can be helpful there. Again, that's just another way to use the double number line. Double number line, in my opinion, has more fluency, more flexibility than the bar model. All right, moving on to the algebra tile technique for this one. 3x minus 5. And that's supposed to equal 13. All right. Okay, I'm going to draw my line down the middle here. Show my equivalency. Okay. Now, I'm on solving this equation. Now, I want to be able to, again, like my algebra tiles up here, I want to be able to split these three up into equal groups here. If I do that right away, I run into some trouble. And this is the idea of why do I want to add or subtract first? Undo is I can't really divide all of this up into three equal groups. But if that worked out, if I hadn't, this might work out really nicely. However, I don't. So what I would like to do is I could, instead of dividing first, we could eliminate the use of these 5, right? I want to kind of like eliminate them. I'd like to not have them here. Let's make each one of these 0. So I could bring in one of its opposites each time to make it 0, right? If I add 1 to this, I get a 0. That's the principle with, say, the balance method, is you take them away, but we want to make it 0. So I'll make 1 0 there, but I have to do that to both sides, otherwise things get unbalanced. So I'll do that, and for every one of those, I will make a 0 by bringing in its opposite. All right, so now I've done that, and now I'm at a place where I can now divide these up into 3 equal groups. There they go. And now we can do the fair sharing right here and see how many we got. So I've got 5 there. And now we can see that we have 6 in each group. We got 1x, 6, 1x, 6, 1x, 6. And so again, we've just solved this equation to say there's 6 in each group there. All right, so again, there's the 3 models. Let's do one more model here, one more model. Or one more example here with all 3 models. Let's make it a little bit even uglier. Actually, let's do one more here, and then I'll turn you over to the other video, which we solve equations with some fractions. But let's do one with negatives, like integers here. Let's make it a little bit easier, just so you can wrap your mind around what to do here. Let's say I have negative x plus 3 and equals 7, because a criticism of the models is that no matter how ugly the numbers get, you say, well, the model will run out. The model won't be useful anymore. And a lot of times I can solve pretty much any equation using all 3 of these models. So let me show you this one here for all 3. I'm going to zoom back in. Double number line being my favorite model with my students. I'm going to draw my number line. I'm going to draw where 0 is. Let's put 0 here. There it goes. And 7 would be over here. Let's put 7 right here. And above it is negative x plus 3. All right, so we've got that. And again, maybe I could double it. We got that flexibility. That's the nice thing about the double number line. But what I could say, well, where is this minus x supposed to be if there was no plus 3? I'd love to know that. This is 3 more than I need it to be to figure out 1x is. So let's go backwards 3. That's why we can say it's on this side of the number line. So we've got, this is 3 more than I want it to be. I do have a negative x still right here, and then that would be 4, right? So I could go back 3 to show that right here is 3 more than I want it to be. I want to know what this thing is right here. It's 3 more than that. I don't want that. Therefore, I've got this relationship right here, and I have a negative x equals 4. Here's the beauty part about the double number line now. It's like, well, what do I do now? Well, think about what's happening right here. This distance on the double number line, this horizontal distance is x units long. It's just saying negative. It's 4 units long. Look at 1. It's 4 units long. That's negative, but it's also equivalent to negative x. I want to know what a positive x is, like what 1x is. Well, if the opposite of x, that's what the negative is representing. The opposite of x is 4 units long. Then the actual x is still 4 units. It's just mirrored on the other side. That's the opposite idea. We've got over here, this is a positive x. That distance right here is the same distance right here. They're just opposites. Like negative 8 is the opposite of 8. Well, they're the equidistant from 0 on the number line. So therefore, what does this number have to be? It's got to be negative 4. And what did we just do? Hey, we just multiplied by negative 1 on both sides. But students have the flexibility to see that. They can say, look, that's clearly got to be negative 4 on the other side. And we've got our solution as negative 4 for x. Bar model becomes a little bit trickier in this regard. All right, I'll draw the first bar to represent the 7, and then I have two pieces that do add to 7. So I have this piece that adds to 7, and I have this piece that adds to 7. I believe we have this to be 3 that adds to 7, and therefore this one is the other piece that adds to 7. And so in the bar model here, you can section off to say, look, okay, well, if this is 3, this is 4, that clearly adds to 7. And right there, you've got your expression that says, well, negative x equals 4. And then now, here's the thing about the bar model is you still have to relate it, when you're working with negatives, you still have to relate it to the double number line of this mirrored version, so that you can conceptually understand that we would say divide by negative 1 or multiply by negative 1 to get the opposite of what we want. That's why I prefer the double number line. The Algebra Tiles is a little bit more seamless, but again, it's not rooted in, say, algebra, or it's not rooted in number sense, because you'll see that we end up just flipping tiles over when we get to that piece. All right, so I have a negative x, and I have plus 3. All right, so I'll draw my equality line, equals. You can do that as well. And then we want to isolate for this. So this is the case where you could say, well, I could just remove them, or I could add their opposite. I tend to make sure that we say add the opposite. And then we get to a point after we've done that, you could remove these. I'll delete those, and I'll delete these just to clear up some space. And now I'm at that spot where I have a negative x equals 4. When I have that. And so when you're working with tiles, this is where it becomes like all of a sudden it's a black box. It's magic. It's hard to explain without the use of the double number line here. If you say, well, negative x is 4, the double number line helps you clearly see why x equals negative 4 because of that symmetry on what the values represent. Here you're kind of saying, well, if the x is 4, then the opposite of x is the opposite of this, and that's a little bit nicer to explain. And so now you have an x equals negative 4 here as another solution. All right, I'm going to zoom out here. Here is all three models, and with the 3 different examples that we were looking at. Don't forget, there's a link down below on solving equations using algebra tiles with fractions. But I'm going to give you a little homework, encourage you to set up a fractional coefficient equation and solve it on the double number line. Think about that fluency. What happens if I have a quarter x? I can quadruple that thing on my double number line to make a whole x. That's really nice. It's a really nice visual showing of the relationships along that line. I want to remind you that there was an activity that goes along with bringing out the idea of using the double number line or the bar model or algebra tiles. It kind of encourages your students to use these models. I'm going to bring up the Make Math Moments tasks website, and I'm going to show you that particular task, and then also show you that we have a full walkthrough of that task. So if I scroll down, now remember that you can search by topic up here. I'm going to scroll down to the shot put task. Okay, so the shot put task is our unit on solving equations, one-step, two-step equations, but then it also goes further into days 5 and 6 on solving using substitution. So it's a full problem-based unit that in the first day we have some video of a man throwing a shot put, and we have to estimate how far he threw. If you head on over to the guide tab, you can walk through those moves. Also in the link below this, I'm putting a full walkthrough of this task from Kyle, so that he walks through how to use this task. We've got a classroom sneak peek in this video. which he did this with students, so you can see what are the questioning techniques there. But you can see that when students are using measuring sticks, the measuring sticks to measure how far this shot put went, naturally leads into representing this with the double number line, or you could be referring to the bar model like this. But we get this nice fluency to think about adding, subtracting, halving, doubling, that kind of thing. So a great task to use when solving equations, and I highly recommend that. We'll put that in the notes right below here. So that's it from us in this particular video. I look forward to your comments below on how you're solving equations, or if you have any feedback for us, we'd love to let you know. Or we'd love for you to let us know, and we will read every single one. All right, we will see you next week in the next video. Take care.